Hi, welcome to Duct Design Tips for Performance and Comfort. And while this is not a duct design workshop, we'll touch on several design principles and I'll refer to ACA Manual D for ducted systems. Now, much of the content in this presentation is based on this ACA Manual D course. The course is actually called Residential System Design for Quality Installation. I strongly suggest if you're going to be designing and installing ducts that you consider taking this online course and buying a good duct design software. It's my hope that you'll find some of the useful information here, but again, it's not a substitute for taking the ACA course. Scott Gibson sums it up nicely in his blog on the Green Building Advisor. Now, there are a lot of new HVAC systems on the market today, and being new, we're learning as we go. People have different priorities and everybody has questions. So one of the HVAC solutions that's gaining traction is ducted heat pumps. Now these systems can really check all the boxes, but the heat pump is only one part of the system. And the other part is a site-built duct system. So there's a lot to know about duct design, and this program is designed to help you get started. So why are we using ducted systems? They give us a whole house distribution. So we're bringing heating and cooling and ventilation air throughout all parts of the home. Also, we can do filtration and humidity control. It gives us a way to run our heat pumps through the whole house as opposed to just, point source heat pumps like you would get with a mini split. So there's a lot of reasons why a duct system is a really good way to go. Well, let's talk about design principles and process. So on the left, we've got a certain number of design things we're trying to get done. Here's our design conditions. We're trying to keep the right temperatures in the room. We want the ducts to be quiet. We want to have minimal air movement where it's going to come into contact with people. We want to have good air quality. So that's what we're trying to do here. And on the right, the ACA Manual D process gives us a sort of 12 steps to accomplish what we're trying to do. So we're going to start by doing a good heat load calculation and getting the number of BTUs we need in each room and locating, we'll draw a plan out, we'll put the outlets on it, and we'll locate the air handler and the trunk lines on the plan. We'll locate any reductions in the trunk on the plan. We'll use that plan to calculate the total effective length of all our ducts and fittings based on the longest run. We'll use that to choose a blower, and we'll calculate the friction rate to size the ducts. So that's the basic process, and those are the basic design conditions. Good duct design starts with right sizing the equipment. Good, accurate load calculations are essential if the goal is to optimize comfort and minimize energy use. And the inputs must be right in order to get a good output. So we have to get all this stuff right. We gotta get the location and orientation of the home. I mean, I'm not going to read everything on the slide, but here's all the essential things we have to get right. The manual J process is pretty careful, and it gives us really good load calculations if it's done right. Let me just say it's not always done right. And the saying is garbage in, garbage out. If you don't put good inputs into your manual J calculation, you're not going to get good outputs. Air leakage has a huge effect on sensible heating and cooling loads, and also a large effect on dehumidification requirements. We have to account for it properly. Many of the rules of thumb, the old rules of thumb about air leakage tightness, are not even close to measured air leakage in today's buildings. Here's some targets that we're using today. So they're given in, the air leakage targets are given in ACH 50 in a lot of cases. Passive House gives us 0.6 ACH 50. Efficiency Vermont's High Performance Homes is giving us 1.0. Efficiency Vermont's RNC base program is 2.0 ACH 50. Arby's is looking for 3.0, although they offer points for tighter construction. These are our air leakage targets. Again, they're given in ACH 50. You may have to convert the units on your air leakage target. So if you're doing your heat loss calculation and your software is requiring CFM50 instead of ACH50, and you know you need 2.0 ACH50 for your target, you'll have to calculate the volume. Be sure to include the volume of air in the conditioned basement. And you can convert them using these formulas. So in the example here, we've got 2.0 ACH50 as our target. So our CFM50 is going to be 2.0 times the volume of the building in cubic feet. So 2.0 times 31,000 divided by 60 minutes per hour. That is going to give us a target CFM50 of 1,033 CFM50. Windows play a big part in the heat load and heat gain in a building. Now it's hard to read the numbers on this graphic, but it's showing that getting the orientation of the building wrong by 90 degrees increased the net heat gain by 28%. This would make a catastrophic difference in cooling loads, and oversizing a cooling system by 28% is probably going to result in poor dehumidification and occupant discomfort and high energy use. And, just let's get it right. It makes a big difference. Now, some manual J programs are going to ask for the R value of a window, but windows come listed with a U factor. And here's the simple relationship. Remember, guessing is not a good option as windows make up a large percentage of the total heat loss and heat gain, or they can, depending on the building. Simply put, the U value is 1 divided by the R value. They are inverse relationship. The R value is 1 divided by the U value. So if we have an R value, or if we have a U value of 0.28, and we need to enter an R value into our manual J calculation, simply 1 divided by 0.28, going to give us 3.57 in this case. Also, another thing to note about windows is the solar heat gain coefficient. The higher the number, the higher the heat gain. So typical solar heat gain coefficients are around like 0.18 to 0.30. You can get much higher ones. You can get them up to 0.6, 0.7 if you want to use them for sort of solar tempered design or some passive solar heating. But in the most cases, it's about 1.18 to 0.30. Higher number means more heat gain from the sun. And here are two labels from Energy Star windows in the same house on different orientations. So the higher solar heat gain coefficient allows more solar heat gain. So you see the one on the left where they have a solar heat gain of 0.51. Those were in south-facing windows. This customer wanted to maximize the input from the south-facing windows. If they were on the west-facing windows, that had a big western view, we could really overheat a house or create significant cooling loads on rooms with high solar heat gain coefficient windows that are pointing west. The one on the right, we see a 0.28 solar heat gain coefficient, which is a pretty normal one. But these were in the same house, so you have to make note of what the solar heat gain coefficient is and which orientation it is. We've done a manual J, and now it's time to do our sizing. So let's talk about sizing a heat pump. We want to consider partial loads. Here's the thing, like high performance homes will see extremely low partial loads compared to typical homes. And when we're sizing heat pumps, the paradox is that we're trying to satisfy design heating loads, which happen 1% of the time, with a system that has reduced performance and capacity at design heating load temperatures. And a lot of buildings have other heat systems that can handle design temperatures. So heat pumps having the ability to modulate and run effectively at part load conditions should use less energy during part load, and maybe we can use something else to satisfy the design load temperatures. It's my little rant on heat pump sizing. Anyways, consider the part loads because we're doing a lot of our heating at part loads and not so much at design loads. Consider the max and the minimum capacity of the heat pump. So that gives us, the range in which it can operate and how low it can turn down. We want to use cold climate optimized heat pumps in order to be able to make heat in cold temperatures. And we want to use a balance point control and a backup system to meet our design temps. Okay, I promise we're almost done talking about heat loss and heat gain, and we're going to get onto ducts pretty soon. So here's a snarky way of saying like this is some stuff to avoid, right? Don't don't start with the number of zones that you need to satisfy with a multi-zone heat pump and just put a mini split head in every room. Um, don't worry about partial loads. If you don't worry about partial loads and you only design for design loads, um, we're not going to have a system that runs steady and can modulate down to the lower loads we need for most of the heating season. Um, we have to look at the max and the minimum capacity. Again, I mentioned that in the other one, but here's one like do not use extreme design conditions like minus 20 degrees Fahrenheit. Um, I think I see a lot of people doing this as a way of providing a safety margin. Well, what if, well, I know it gets to minus 20, once in a while, but if we use that for our design conditions, we're going to end up like oversizing our equipment. So let's get it right. So let's use the right design temperature. This is a chart from an ASHRAE tool that I found online that shows design weather data for most cities in the country. And I looked up Burlington, Vermont. And boy, I was surprised to see that design conditions were minus 19.7 degrees. So no wonder everybody uses minus 20 design temps. So what are the design conditions for Burlington, Vermont? I guess it's minus 19.7 if you're using Celsius. Otherwise, minus 4 Fahrenheit is the right design temperature to use for Burlington, Vermont. Well, that's enough about heat load calcs. Thanks for sticking with me while I go on and on and on about proper sizing. I guess my point is that getting the loads right really helps us design the right duct delivery system. Now, this next section is about ducts design. Here's some of the things we're going to talk about. We're going to talk about getting the CFM right and delivering the proper amount of BTUs that will meet the loads in each space. Equivalent length is going to give us the pressures that we need. It's going to help us determine our friction rate. Friction rate is used for sizing the ducts. We'll discuss static pressure and the blower capacity and how it affects the blower. We're going to talk about sizing the ducts using duct calculators. I'll give you a little bit of tips on how to decrease the noise, make sure that everyone's comfortable and have a very efficient system. So we're going to start by getting our BTU loads for each space. So the block loads we do for the whole house system sizing, and then we do room by room loads for distribution. So we're going to have to figure heating loads and cooling loads, and then we determine the CFM requirement for each room based on these loads. And the CFM is basically it's the sensible heat output times 1.08 divided by the delta T, or the temperature difference across the heat exchanger. 1.08 is this air constant based on specific heat of air and the weight of air. It helps to understand the relationships when we're talking about CFM. So for the whole building, again, it's a sensible BTU output divided by 1.08 times the delta T. So an example for a 3-ton heat pump would look something like this. So 3 tons or 36,000 BTUs divided by 1.08 times 30. So that's going to give us a CFM of about 1,111. Now remember that delta T on a heat pump is about 30 degrees. And this is significantly different than the 50-degree delta T on a furnace. In most cases, we're going to need to move more CFM to achieve the same BTU output when we're using a heat pump versus a furnace. And this comes into play when we're trying to calculate the CFM for a dual fuel system. Now, again, like I mentioned, a ducted heat pump is going to have a delta T across the coil of 30 degrees. And The heat exchanger on a furnace might have a delta T of something like 50 degrees. So, I mean, if we do the math and we use the same 3-ton example for the furnace, we're going to need 667 CFM. So, size for the heat pump or the higher CFM requirement. If we undersize the ducts, in other words, if we design the ducts for the furnace and we have a dual fuel system where we're using a furnace and a heat pump sharing the same ductwork, we're going to undersize the ducts if we size it for the furnace. Those undersized ducts are not going to deliver the required amount of CFM when we're running our heat pump. So designed for the larger CFM requirement. So we're still looking at relationships of CFM. The CFM, also known as the volume, is equal to the area times the velocity. So the CFM delivers heat to a room. That's why we need our room by room heat loss and heat gain calculations so we can figure out how many CFM to put into the room. And the amount of CFM we're able to bring into that room really depends on the blower capacity, the size of the duct, the speed of the air moving through the ducts, and the temperature of the air that we deliver to the room. Okay, let's talk about velocity for a minute. Velocity is part of the equation that we saw before. Here's a different way of looking at the same equation. We define velocity as the speed at which air moves through the system. And there are some guidelines for how fast we want the air to flow through the trunk ducts and how fast we want it to flow through the branch ducts. Uh, in the trunks, we want it around 700 to 900 feet per minute, and in the branch ducts, something like 400 to 600 feet per minute. If the velocity is too low, the air is not going to mix in the room. Like we're not going to get enough flow out of our registers to mix the air in a room, and we're going to have stratifying temperatures. If it's too high, we're going to make noise, and people hate to hear the noise from the air system. So if the velocity is too high, we're going to hear the air whooshing across the registers. That's going to make people unhappy. It's important to get the balance right and get the velocity right. Well, velocity will have an effect on the air delivery. For example, we can use the velocity to help size a branch duct, right? So our guidelines recommend 400 to 600 feet per minute in a branch duct. And we know if we want to get 100 CFM out of a register that's being supplied by that branch duct, then we have these equations that give us the relationships between velocity and area and CFM, and we can solve for the area. So we also want to use balancing dampers to fine tune the volume. So by using the balancing dampers, we change the area, and that has an effect on the volume and the velocity because they're all related. Be sure to keep those dampers accessible so that we can actually use them. Well, why does velocity matter? Um, so velocity allows us to choose the right register. It allows the right air mixing of air in the room. I think it's important to note that when you feel the air blowing out of a register, you're feeling the velocity. You're not really feeling the CFM or the BTUs. You're feeling the speed of the air. And it's good design practice to keep the velocity the same at all the registers. Um, People don't like too much discrepancy between the outlets, that it gives the appearance that something's wrong with the system. Um, we want to keep the velocity low because it makes noise. At, at filtered return outlets, we want to keep it below 350 feet per minute. We also use the velocity to place the reducers in the trunk, which gives us better airflow in the registers that are close to the blower. And we place those reducers at half the initial trunk velocity. Let's talk about how pressure affects the system. It's good to understand the relationship between the pressure and the blower. So if we think of the blower, it's a pressure increaser. And if we think of like all of the ducts, they're all pressure decreasers. So the static pressure is the pressure of the air not moving. That's the pressure that the blower is pushing against. And the fan uses about 80% of its energy to overcome this, to push against the pressure, and only like 20% to actually move air through the ducts. And this is why when you look at the SEER ratings on heat pumps, like the ductless mini splits have better SEER ratings because they don't need to push against the duct system. They don't need to push against the static pressure within a duct system. So we don't have all of that fan energy being wasted or being used to overcome the static pressure in the system. With a PSC blower motor, the increased load will decrease the RPMs and therefore the CFM of the blower. For electronically commutated motors, the increased load causes the motor to ramp up speed and it'll increase its RPM and use more energy. So it's really important to know the loads and keep within the targets for your blower. Pressure is measured in inches of water column. And everything you put into a duct system is going to add pressure drop, which is sort of like a parasite. It kind of robs the system of its pressure that it needs to move the air. So everything adds a pressure drop. The filters, the AC coil, all the fittings, the registers, the dampers, the ducts, etc. Now the blower gives us a pressure rise, and all the ducts and fittings are a series of pressure drops. Now we got to have balance, right? The pressure drop can't exceed the pressure rise, or we won't get the CFM we need out of the system. Toots and the Maytals. Toots did a great song about pressure drop. It went to the top of the charts, and millions of people loved it. And that's how important pressure drop is, right? It's a big deal. People write songs about it. The available static pressure is what's left over for the ducts. The blower is going to create a pressure rise, and it's rated for a certain amount of airflow at a certain pressure. And the ducts and the fittings and the registers and the balancing dampers and all the other components in the system all cause pressure drops. So you have the pressure rise by the blower trying to balance out with all the pressure drops from the system. And if you extract the pressure drops for all the things that aren't ducts or fittings from the total external static pressure, that's going to give you the available static pressure, like what's available, what's left over. And the available static pressure is sort of like the budget that you have to work with when you're trying to select your ducts and your fittings. So here's how we come up with our available static pressure. So in our example, we're going to look up a blower, look up the data on a blower, and we're going to find out that it can move 1200 CFM at 0.8 inches of water column. So with 0.8 inches water column of pressure in the duct system, we'll be able to get 1200 CFM out of that blower. So what we do is we start with our capacity, which is 0.8, and we subtract some of the stuff that's not ducts, right? So the evaporator coil, the air cleaner, and the registers. We subtract the pressures from all those things, and that's all listed in the data for those components. And we find out we have 0.21 inches of water column of available static pressure. And that's what we're going to use. We have to design a duct system that'll work with 0.21 inches of water column. Well, the total equivalent length, also known as the effective length. When you add up the effective lengths of all the fittings and then add that number to the length of the straight sections in the most restrictive runs in the return and supply ducts, you find the total effective length. So like the critical path is the longest path that the air needs to flow, which means the path with the most resistance in it, right? And we use these total equivalent length to calculate the friction rate when we want to size the ducts. We use the total equivalent length to calculate friction rate. And then we use friction rate to calculate duct size when we use a duct calculator. Here's the formula for calculating friction rate. It's just the available static pressure times 100 feet divided by the total equivalent length. Friction rate's given in inches water column per 100 feet of equivalent length. And you have to use the calculated version when you use these duct calculators to size your ducts. Because if you assume the friction rate is 0.1 inch per 100 feet, You may or may not be right. So here's an example. If we use zero point 0.1 instead of the calculated 0.06 inches, that's going to give us a duct size that'll deliver 900 CFM versus the 1200 CFM that we wanted. When you calculate the friction rate for a particular design, you're finding out how much pressure drop you can get away with for each 100 feet of effective length of your duct system. If the friction rate is higher, you can use smaller, more restrictive ducts. And if the friction rate is lower, you want to use larger ducts. Hopefully that makes sense. Here's the duct calculator. Let's say we're looking for 400 CFM in a duct. We line up our friction rate of 0.73 with 400 CFM, and the duct calculator tells us that we can use 10-inch round sheet metal duct or 12-inch flex duct if we're using flex duct at 4% compression. So again, here's our 0.73 and here's our 400. And when we line these wheels up so that those points meet, this over here tells us that we are looking for a 10-inch round sheet metal duct diameter. Here's a different part of the duct calculator that we use to figure velocity. The duct calculator gives us velocity at a given CFM for a specific duct size. And we need to check the velocity to make sure it's not too high or too low. In this case, 400 CFM gives us 725 feet per minute, which would be fine for supply trunk ducts where the max is 900 feet per minute. But if it was a return trunk, we'd want less than 700 feet per minute. So in this case, we would increase to a larger duct. We'd go up to the next size, which is a 12-inch round in this case. Here's a few takeaways from the last section. Let's remember that we want to size dual fuel systems for the highest CFM requirement. Let's also remember that people feel velocity, right? We don't feel CFM coming out, we feel the speed of the air. And too much velocity makes noise, which people don't like. Remember to use the calculated friction rate when you're using duct calculators for sizing ducts. Don't assume you know the friction rate. Always calculate that. And use balancing dampers. Put balancing dampers in all the branch ducts and make them accessible so people can commission the system. Don't forget pressure drop. Pressure drop has to be equal to pressure rise. It's really important to make sure we know what the pressures are in the system. Indulge me while I go on a little tear about flex duct. So I think flex duct could be called reduced flow duct. Now, in reality, if you do flex duct properly, it's actually pretty good. It tends to have less duct leakage than standard duct. But to do it properly, I think would be cost prohibitive. If you were to really stretch it out tight and support it every 48 inches with a strap, I don't think I've ever seen this. But if you were to do it properly, I would submit that it would probably be more expensive than using regular metal duct. So here's how we see reduced flow and flex duct. So with it pulled tight, let's say we can get 110 CFM out of a 6-inch flex duct. If we have 4% longitudinal compression, that's down to 70 CFM. And with 15% compression, we're down to 40 CFM. So you can see like more compression equals fewer CFM. And that's on a straight run. So that's before we start making turns with it. So, you know, I think, okay, use it for straight runs with the inner liner pulled out, but maybe don't use flex ducts for turns. And don't use flex duct like this. Let's talk about fittings. They have an effect on the pressure. everything in the system adds pressure drop, right? So we want to design our system with minimal fittings because more fittings add up to more pressure drop. Look at the effect of the throat on this elbow here. On elbow A, we have a square throat, and the sharp corner here at the throat creates turbulence. So all this air eddy behind this corner. Now the airflow through the elbow has to fight its way past that turbulence. So the air carrying capacity of this elbow is less than the air carrying capacity of this elbow, which has a radius through, right? So less turbulence, more airflow on the back side of it. If we look at the chart up here, we can see the radius with respect to diameter. So let's look at, for example, this 4 or 5 piece elbow. At 0.75, the radius at 0.75, the diameter, this piece here is going to give us 30 feet of equivalent length. And if we upsize this radius just to 1.0 times the diameter, it's already dropped to 20, and 1.5D is down to 15 feet of equivalent length. Let's talk about the fitting shape and its effect on pressure. When we have air going down the trunk and it comes to a takeoff, like a right angle takeoff, the throat shape has more effect on the turbulence than the heel shape. So let's look at how much effect that has. On a 8x14 elbow, if we're looking at 500 feet per minute of velocity, the square heel, square throat elbow has 39 feet of equivalent length. The radius heel, square throat has 36 feet of equivalent length. The radius heel, radius throat is down to 13 feet equivalent length. So there is a difference between the throat radius and the heel radius and the effect that they have on an elbow's ability to move air. A couple more words about elbows. This really grainy picture still does a great job of illustrating what happens without design and planning. I suspect the system was probably not planned this way. I believe this was the installer's idea. But I think what happened was we didn't have a plan here. We didn't have a good plan on how we get over that big steel beam. There wasn't room above the trunk to do the takeoffs that would go over the beam, or perhaps there was something blocking us from going over the beam. But look at all the elbows, and knowing what we know now about the pressure drop of each one of those elbows, how good do you think the air delivery is in that system? Are we getting the CFMs we need? This sketch really does a nice job of showing us where the turbulence is. If we look at the turbulence here, this one with the square throat and square heel, we see turbulence built up on both sides. If we look at the turbulence on this one with the radiused heel and the square throat, we see turbulence built up on the back side of the throat. If we have a radiused throat and a square heel, we see less turbulence behind the throat, but a little bit out here in the heel. And we can see the equivalent length is reduced every time we do something to this fitting. So remember we saw before the effect of the throat versus the heel. Well, here it's showing up again. And if we put turning vane in here, this basically, uh, it's like 4 or 5 blades that, that take the airflow and they break it up into 1.5-inch slices, and they move them around these curved vanes. So in this case, we only have one of these 1.5-inch slices that's affected at the throat and only one that's affected at the heel. So the rest of the airflow is not caught up in all of these other turbulence and is free to flow through. So that's why we get so much less equivalent length if we're using turning vane. Again, the turning vane is a great way to reduce the equivalent length on square elbows of rectangular duct. Here again, another view, all the turbulence, and here we are at the turning vanes. In this next section, we'll talk about registers. Understanding the registers helps us design a system that will deliver the right amount of air without blowing directly on the occupants, keep things quiet, and put the air where we want it. Let's talk about some register definitions because that'll help us design properly. The face velocity is the speed of air as it hits the face of the register in feet per minute. That matters. We'll see that come up. The area is defined as the AK, which is the free area in square feet. Now remember, if we're using the area of a register for a combustion air louver, that's in square inches. So we would need to convert that if we're going to use this AK number for that purpose. But for the purposes of designing registers, we use square feet. Remember that relationship between volume and area and velocity? Well, that's also used to size registers, and that's why we need to understand the face velocity and the AK because that helps us work this out. Surface effect is simply the fact that airflow will tend to remain in contact with the surface. So if we have a ceiling diffuser that's turning the air to push it across the ceiling, that air is going to want to stay in contact with the ceiling before it just falls off. Here are some more register definitions. Some more terms that we should understand for selecting registers. Terminal velocity, right, is the speed of the air at the end of the throw in feet per minute. So terminal velocity is about 50 feet per minute, sometimes 75 feet per minute. It's usually listed on the register table. To put that in perspective, like you can smoke hangs in the air at something less than 15 feet per minute. When we start getting into 15 and above, we can see smoke start to move in the air. It takes 65 feet per minute to blow a paper off of a desk. So that maybe that helps put it in perspective what terminal velocity we're talking about. Throw is the horizontal distance that air travels before it reaches terminal velocity. So once a register has a register will be spec'd to have a certain throw. So when we know the velocity and the register type, we'll be able to tell how far we can push the air out before it reaches terminal velocity. And this gets important when we start talking about not blowing air on the occupants, right? The spread is the width of flow at the end of its throw or at terminal velocity. The drop is the distance the air drops at the end of the flow. And there's this principle of induction and aspiration. So the primary air is the supply air that comes out of the outlet. And the secondary air is the room air that gets pulled into the primary airstream through the induction aspiration process. It's important to note that the primary air induces like 10 to 20 times more secondary air. So the secondary air is going to create, 10 to 20 times your airstream in the room. And the primary air is just what's coming out of the register. So the occupied zone is where the people are. A good duct system will move air outside the occupied zone so as not to blow air directly on the people. Air blowing directly on people creates discomfort and dissatisfied customers. So use the surface effect to wash walls and ceilings with air and avoid moving air in the occupied zone, which is defined as from the floor to 6 feet above the floor and greater than 2 feet from the outside walls. We want this area to be comfortable. Don't blow air on people. So think about it this way, like air in the occupied zone should move at terminal velocity or slower. Let's talk about selecting registers. Everything you need to know for good design is on this chart. Okay, so like if we are selecting a register, maybe we want a 10 by 4, we know we have 500 feet of face velocity. Here's the 10 by 4. Here's the free area. So this gives us the CFM we can get, 100 CFM, and here's the throw, 9.0 feet. And that's based on, remember, it's going to show us a terminal velocity here. So at the end of 9 feet, that 10 by 4 register is going to be moving at 75 feet per minute if we feed it with a face velocity of 500 feet per minute. And this is the profile here of a deflection A profile is this one where all the fins are pointing straight. And you can see this is not a very big spread, but a big throw. And this NC 30 noise coefficient, less than or equal to 30. This is where we want to be. So on the chart, all the white stuff is the go zone, and all of the gray and dark stuff is like we're going to have more noise there. So maybe in some places like a laundry room or some place where people don't really care about the noise, that would be okay. But for most places like offices and residential rooms, we want to keep the NC under 30. Here's a couple of um, different deflection patterns, and you can see how they affect the spread and the throw. So basically what we're seeing here is that like more spread equals less throw, right? Here's some guidelines for keeping noise down. Remember, more velocity means more noise. And registers have a listed noise coefficient. We want to keep it like below 25 or 30. Um, if we have a blower, if we have a register that's too close to the blower, we're going to hear it. One possible solution is to put a couple of 90s in that branch duct, and that can have the effect of reducing the noise by half. Remember, it's going to add equivalent length to the system and that adds static pressure. But if noise is a concern, that's one way to take care of it. Another way might be to put duct liner in the first maybe 5 or 10 feet of the trunk duct. And that's great, but duct liner reduces noise but adds friction, significant amount of friction sometimes. So if we place the first couple takeoffs, 2.5 to 3 duct diameters, or maybe 5 feet from the plenum, that's going to help quiet them down a little bit. We want to leave 2 to 3 feet between takeoffs. Remember, if sound can be transmitted, if we have 2 takeoffs that are directly across the trunk from each other, especially when the air is not moving through the ducts, those can be like really good sound transmitters between rooms. So we want to make sure we leave a few feet between the takeoffs and don't put them right across from each other. Curved blade diffusers will have a lower noise coefficient. So that's always good to know. Curved blades move the air more smoothly than flat blades. Never place a branch line directly on a plenum. The plenum has a much higher velocity than a trunk duct. So we want to make sure we don't do that. And never place a register too close to the blower. I think we already mentioned that one. And here's some guidelines for return air. So returns do not have much effect on a room's air movement, regardless of the face velocity. They only grab air about a duct diameter away from the face, and most of the room air movement is done by the supply ducts. Return grills work because they create a negative pressure, and the air in the room moves towards that negative pressure at terminal velocity or less. So it's not, the return grills are not like sucking air. It's not a good way to move air somewhere. Um, don't put returns in the kitchen or bathroom because that's where the smells are, and you'll just be distributing the smells nicely throughout the house. We have some recommended 300 feet per minute for filter grills and 500 feet max for non-filter return grills. And that filter gives you more impedance to airflow, which is going to make more noise at higher velocity. And at least one return on every level. So don't put the return only on the first floor, nothing on the second floor. Here are some more return air guidelines. this time pertaining to filters. So I think the big one is don't hit the filter at an angle. Make sure that the airstream hits square to the filter. If the filter's tipped at an angle, it actually creates more impedance to the airstream, which makes more noise. So we want to keep the filters out of the turbulent flow. So we don't want to install the filter near an elbow. Remember we saw where the turbulence is, like right behind that elbow. We don't want to do that. We want to keep them out in a straight run if that's at all possible. We want to make sure they're easily accessible. We have to account for the pressure drop if we're going to upgrade the filtration on a system. We will want to make sure that the system has enough um, ability to overcome the static pressure of the higher filtration media. Um, an ECM blower will use more energy to keep the flow rate up, and a PSC motor will lose CFM. So and this is regards to dirty filters. So an ECM blower motor with a clean filter running at 0.2 inches water column and a 1100 CFM is going to draw about 225 watts. If that filter gets dirty and now we have 0.5 inches water column, we're still going to get 1100 CFM because that ECM motor is going to ramp up to overcome the pressure of that dirty filter. And it's going to use 320 watts. So, I mean, maybe that's okay. We're going to use more wattage, but it's still going to be able to do the work. With PSC filter motors, permanent split capacitor motors, the air handler, the flow would be reduced, right? So it doesn't have the capacity. It feels that pressure. If it feels too much static pressure, it just ramps down. It just has the effect of like, okay, well, it's just gonna overcome the power of the blower. And in that case, we might use a little less energy, but we're going to move a lot less air, in the magnitude of 40 to 50% less air. So if we're not moving the right amount of CFM to the room, like what's the point? Here's a note about ECM blowers. If we look at, say, a 1/3 horsepower permanent split capacity motor, um, and we have a design CFM of 1,000 CFM, and our static pressure is 0.3 inches water column, it's going to deliver 1,000 CFM, and it's going to use 335 watts. If we use an ECM motor um, designed for 1,000 CFM at 0.3, it's going to deliver 1,000 CFM at 225 watts. So the ECM motor is more energy efficient when it's at design static pressure. If we take those same two motors and we increase the static pressure to 0.6 inch water column, the PSC motor is only going to be able to deliver 400 CFM. Now it's going to ramp down, so it's going to use less energy, but it's only going to deliver 400 CFM. And if we need 1,000 CFM, that's going to be a problem. On the other hand, the ECM motor at 0.6 inch water column is still going to deliver 1,000 CFM, but it's going to use more energy to do it because it's going to ramp up to overcome that static pressure. And here's another thing we may want to consider is that if we're using a ducted heat pump with a PSC blower motor, like say we put a ducted heat pump on a existing furnace that has a permanent split capacitor motor, and the blower is only delivering 400 CFM due to that 0.6 inch water column, the ability to move heat is cut by 60%. And that excess heat builds up in the cabinet and gets returned by refrigerant to the compressor. Now the heat pump runs at high temperature and refrigerant pressure, returning more heat to the outdoor compressor. It runs longer and harder with reduced efficiency, both because it's trying to heat refrigerant that's already hot and because the heat isn't getting to the home to satisfy the thermostat. And even if we're using more wattage to overcome friction on a dirty filter, it's essential to have the ability to deliver the design CFM flow for the longevity of our compressor. ACA manual D process. So we've been through all of this in the training. We talked about the manual J and assigning a CFM for each room, locating the outlets and drawing the trunk lines and branch lines. We've discussed all of this stuff at length so far. And what we haven't discussed is what happens next. If it were up to me, step 13 in the ACA manual D process would be commissioning. A few thoughts about commissioning. Commissioning is essential. I mean, without measuring the flow and adjusting balancing dampers, we don't know if the system is actually going to deliver as it was designed. And this step is tragically overlooked on many jobs. Here's an example of an air balance test report. This is a simple commissioning checklist. Each register or outlet gets assigned a number, and we write down the room that it's in. And then we know from our manual D design what the CFM flow should be in that room, and we test. So you just go around and test the whole house without adjusting anything. What do we got? And you can look at that, and you can look at that and compare it to the plan and say, okay, well, we need to move this one a little bit and that one a little bit. You make some adjustments, and that's what you put in, and then you test again after you make your adjustments. So you can't just make adjustments and walk away, open it up a little bit and go, there you go. There's a little more flow for you. You got to put the new numbers down, test the whole system again, because when you change one part of the system, it changes everything. And then, the final column is in case you need to do it again. And here's the thing, use balancing dampers to adjust the airflow and not the registers. I'd like to introduce the concept of simplified duct systems. Many of today's homes have really superior enclosures, and they don't need supply air delivered under every window like old houses did. I mean, the windows are much better. The wall insulation and air tightness assemblies is a whole other league. And these houses have very low loads. So consider the benefits of a simplified duct system like the one shown on the right. So fewer materials means lower installed cost, and there's fewer soffits and duct chases, but mostly these systems just result in better performance. Even the standard system that you see on the left would be a huge improvement over what's being installed today due to its relative simplicity. Simple trunk layout, no branch duct elbows, etc. Everything is like straight and easy. I would say be careful to avoid the occupied zone with these. I think the temptation here on the high efficiency system on the right would be to install high wall registers, and those would tend to blow out and blow into the occupied zone. So be careful of that. We don't want to blow air directly on people. And this is especially important when we're designing for ducted heat pumps in a high performance home. Heat pumps have a lower delivered air temperature and higher CFM rates, remember? So it's even more uncomfortable for occupants in contact with that airstream. So do a good job of keeping the airflow out of the occupied zone. Integrating the ventilation ducts. Let's talk about combining ventilation system ducts with space conditioning ducts. In general, ventilation air requirements are much lower than airflow required to heat and cool a space. But as heating and cooling loads get smaller and smaller due to more robust building enclosures, we find that combining the two duct systems starts to make sense. Integrating the ventilation ducts. Dedicated stale air exhaust from bathrooms and kitchens is an important part of integrated systems. And although often cited as a design option by HRV manufacturers, connecting exhaust and supply air to the air handler trunk ducts creates short cycling and poor ventilation. So there is a better way. And Bruce Manclark hit it right on the head with his 5 golden rules for HRV duct integration. Number 1, always connect to the forced air supply ductwork, not the return. And the way to do that is number 2, always use the injection port design. I'm going to show you that in the next slide. Number 3, choose an efficient HRV. Efficiency Vermont has a qualified product list of efficient HRVs with ECM motors and very high recovery efficiency and good cold weather defrost strategy, consider picking one from our qualified product list. Number 4, buy an electrically commutated air handler motor. So we want the blower in the air handler to have an ECM motor. Number 5, pull exhaust air from the bathrooms. So that's the dedicated stale air exhaust from bathrooms and kitchens. And here's the injection port. What it is the fresh air from the HRV is coming down through here and dumping out of this elbow into the duct trunk. The front of the duct trunk has been removed here so we can see what it looks like. This actually is really effective. The airflow in the trunk pulls the air off the end of this elbow and mixes it in nicely. I think I want to caution you that, we need the injection port, meaning this elbow piece down here. And then if we just had a takeoff collar here and no injection port, the blower on the air handler would overpower the blower on the HRV, and we wouldn't really get any ventilation at all. In the past, installers have been, and presently, installers are putting the supply air from the HRV into the return side trunk. And Bruce Manclark takes exception to that, saying that he thinks that's leading to overventilation, that there's so much suction on the return side of that main trunk that we're pulling way more air than we need to through the HRV, and we're creating overventilation. Why we want to use an ECM blower. When we're combining ECM blower and an HRV, imagine that this large old school PSC air handler with a single speed blower is moving a small amount of fresh air continuously. That makes no sense, right? So remember that those old PSC motors use like 300 to 600 or more watts. So having that run full time to do a low flow continuous ventilation system doesn't make any sense at all. Use an ECM motor. A 16-pin ECM motor can run as low as 40 watts. And this creates efficiency gains even over the 13-pin ECM motor, and is light years better than the PSC motor. The ECM motor can be controlled, several different speeds. It's nice to run the ventilation down on low speed. ECM motors are way more efficient, especially when they're properly controlled and running at a lower speed. I say if you can get this deep into it, make sure you're using the 16-pin ECM because it is more efficient than the X13 ECM when we're talking about the air handler blower. Consider an ECM air handler blower a necessity when we're combining ventilation and space conditioning ducts. Here's some ventilation control strategies. The first one being continuous operation, right? So both the HRV and the air handler are running on low speed continuously. Use a smart controller to boost the flow of the air handler fan when heating or cooling, but have it be running on low speed in the background to help move the ventilation around. This means there's less noise and a better mix of ventilation air with house air, which helps give us a more comfortable delivered air temp. So if we're mixing a little bit of house air in with the ventilation air, we're actually warming up the temperature of the incoming ventilation air, like say in the wintertime. Remember those 16-pin ECMs can go way low, right? So 40 watts for an air handler, pretty nice. Number 2, the HRV controller operates the air handler blower only when ventilation is called for. So be sure the HRV has dampers that open only during ventilation. Otherwise, air could flow in reverse through the HRV when the air handler is running. So we don't want to be pushing air outside, our heated air outside when the air handler is running if the HRV is not running. So you can use demand control options for this, like to trigger the ventilation events using a CO2 or VOC sensor. Number 3 is interlocked, right? And ventilate whenever heating and cooling, and run the air handler whenever the HRV is running. So this is the two interlocked together. So if we're running heating and cooling, we're ventilating. And if we're ventilating, we're running the HRV fan. This maximizes the distribution and make sure that all heating and cooling runs include some ventilation. Uh, in this case, we would use a smaller HRV and we would use bath fans to ventilate the bathrooms. Let me introduce you to the HVAC pod. This is a great way for us to put the air handler and the HRV and a water heater all in a small closet. And this idea was born for use in the zero energy modular homes that have a very small mechanical closet. And this allows everything to coexist in a very small space. And testing has shown this type of injection hood is very effective. This sort of hood port versus the elbow port that I showed you earlier. So this is a great way to put all this stuff together in a nice tidy package. I do want to just show you that, find the laser pointer here. I do want to show you that my colleague Peter Snyder, who did this SketchUp plan, I asked him, I'm like, hey Pete, shouldn't we use like a curved vein here? Wouldn't that, be better? And he said that this system has a curved vein in it. He just couldn't figure out how to draw it in SketchUp. So I just imagine this is a nice gently swooping curve on each of these two veins here. But this is your main duct trunk here. And your air handler is here. And it pushes air out here across the injection port where it picks up ventilation air. And then the two air streams are routed down this long trunk that lives in the upper corner of the ceiling. The HVAC pod. Here's another look, another schematic, and again on the right, here it is in real life. The MERV 13 filter is located above the closet door. Let me get my pointer out here. You can see that. So here's the filter. We're using a good MERV 13 filter right here at the door, easy to change. Then here's the small return plenum here. This is the air handler from the heat pump. And here is a small supply duct plenum. And here is the main supply duct going out this way. This is the ERV. The fresh air goes through the injection port right here into the supply plenum where it's mixed with the air from the air handler and goes out into the supply. This duct here is the return air, dedicated returns to the kitchen and bathrooms. And that goes into this side of the ERV. And then here are our two ports going outside. This is a heat pump water heater. And there is a return. There's a small return outlet. Well, you can't really see it in this picture, in the closet, which actually creates a slight negative pressure in the closet and brings house air underneath the undercut door to feed this heat pump water heater. And what that does is it keeps the water heater from cooling down this room to the point where it can't really work effectively. Whole package works together very nicely. Here are some of the specs on the HVAC pod. We can see the heat pump is the new higher Arctic next generation 12K using the MSD, the mid static duct air handler. This heat pump is rated for minus 31 degree Fahrenheit operation. So serious cold weather application. It's got 100% capacity at minus 15, and we're thinking it doesn't need electric resistance backup of any kind in this small high performance home. It's being controlled by a wall mount thermostat. This MSD duct, this MSD air handler has a low speed of like 264 CFM, and the turbo high speed is just under 500 CFM. So you can see that with the loads being small and the ducts being simple and straight, we really don't need a ton of CFM to deliver into this small modular home. The HRV or ERV, I guess, is a Life Breath Metro, and that's, let's see, that's the 120 ERV-D. So this has a special defrost capability, a good cold weather defrost, and an ECM motor. The home had a 60 CFM design requirement, and I believe this thing is capable of 114 CFM at 0.4 inches water column. That should be 0.4 inches, not 0.4 feet. The bathroom and kitchen, dedicated exhausts, and the bathroom has a high-speed boost. So if you go to the bathroom and you shower or you need ventilation, it turns the whole system onto high. The fresh air injection port is downstream of the air handler, so the air handler doesn't need to operate on a ventilation call, right? So the fan on this Life Breath Metro is big enough to provide the ventilation that we need in this home and using this small simplified duct system. And we don't need to interlock with the higher. So that's pretty cool. Again, the Ream 65-gallon heat pump water here. And we're using a CO2 demand control to trigger ventilation events. So it's going to run on low speed continuous using just the fan from the Life Breath until we have a ventilation call either from the boost or from this CO2 demand control, in which case the interlock system comes on. It gets a little boost from the MSD air handler, and that's how it works. A little bit about the HVAC pod control strategy. Again, the ERV runs on continuous low speed with a CO2 demand control boost. So there's a CO2 sensor that tells it when the CO2 levels in the house are too high, and it goes into boost mode where it runs until it brings the CO2 levels back down below the set point. There's a boost control in the bathrooms like we discussed. So for the most part, the air handler is disconnected from the ERV except for boost mode. So when we have a boost from the CO2 control or from the bathroom control, the HVAC air handler interlocks with it and gives it a little bit of help. And this works because the ZEM is a small home and it has a simple duct system that allows adequate ventilation flow without the air handler. Now remember, with low load homes, the home doesn't have much heating and cooling loads, so the duct system won't need to move 1,000 CFM. In this case, the air handler is designed to move something between 250 and 500 CFM approximately. So that's more closely aligned with the CFM requirements of a ventilation system. In a larger home, the air handler would need to operate all the time in order to achieve adequate ventilation, in every part of the house. And here's the schematic. Remember, this zero energy modular is a mobile home replacement. So it's all laid out very linear, which lends itself well to this strategy. Let me get my laser pointer out again. Here's the mechanical closet right here. And we saw what that looks like in previous slides. Note the proximity between the mechanical closet and the bathroom and the kitchen, right? So we want dedicated stale air from the ERV. See this E here, this is exhaust. We get really good proximity to these two rooms, so the ducting is minimal between for the dedicated return ducts. The supplies, just as we described, it goes small plenum from the air handler into the main trunk, picks up the injection port on the way to get ventilation air, and it goes out, it tees off and goes in two directions. Simple supply. And these are supplies in a soffit that's built between the wall and the ceiling in the upper corner of that wall. Here's a photo of the duct trunk in a soffit with an example of a simple takeoff and a register. Notice that the ducts are sealed and insulated, and the duct trunk was built after the drywall was hung and taped. This we do in order to minimize heat loss to outdoors. Remember, we're trying to keep all the ducts within the conditioned space. So if they want to be 100% in the thermal enclosure, that means that the drywall air barrier has to be intact on the backside of the soffits. So we don't have a leaky air pathway to outdoors in our duct soffit. Here's a couple more photos of the trunk. You can see behind the completed soffit, this home is still in the factory, so you can see out the window, there's the factory. Here's our soffit here. Here's our duct trunk behind here. It's really inconspicuous up here in the corner. The the registers here are going on, and they're designed to move air across using the surface effect across the ceiling. So they blow out this way up against the ceiling. And by the time the air drops, it's moving slower than terminal velocity. So it's not blowing cold air on people. Here are the two, the larger main trunk size, and then the smaller stale air pickup size, the exhaust air from the kitchen and bathrooms. Both of those ducts live in this one little trunk. RBs. So many of you know the residential building energy standards are getting an update for 2019. Well, I should say 2020 because that's where we are now. Goes into effect September 1, 2020. And they have some rules about ducts. So ducts and air handlers for space conditioning shall be in accordance with sections 403.3.1 to 403.3.5. So get familiar with those sections. Basically, they are requirements for duct insulation, um, duct sealing, duct testing. Uh, Duct sealing is required no matter where they are. Insulation and testing are required if the ducts are outside the enclosure. I will say that if you are working on a home that's enrolled in the Efficiency Vermont's residential new construction program, ducts are not allowed outside the enclosure. So you don't have to worry about it there. Just don't put them outside. You shouldn't put them outside anyway. And the building cavities shall not be used. So this is new. I think it um, used to allow building cavities for return ducts, but now that is completely out. Now remember, these code requirements are based on sound science and the principles of all the manual D stuff we learned in this workshop, and it's not an unnecessary regulation, it's common sense. Building cavities shall not be used. So the National Fire Code and the IBC both state that no combustible materials. And that includes building cavities, and that includes you can't run wires and pipes through your ducts. Um, and even if this requirement isn't specifically enforced at the local level, by law, the HVAC contractor is still liable in the event of a fire. Um, Panning is not recommended by Manual D. So just, please just stop doing this. Thank you. A little bit more on RB's 2019. R403.7 says equipment sizing and efficiency rating is mandatory, right? So heating and cooling equipment shall be sized in accordance with ACA Manual S based on building loads calculated in accordance with ACA Manual J or other approved heating and cooling calculation methodologies. So, I mean, right, do a good heat load calculation. That's just common sense. It's what we know. Make sure this gets done. New or replacement heating and cooling equipment shall have efficiency rating equal to or greater than the minimum required by law for climate zone 6. So don't put in terrible equipment and, do a heat load calculation. That's all it's saying. It's just common sense. And one more thing on RBs. Any resistance heating intended to supplement heating capacity at very low temperatures is disabled by controls above 5 degrees Fahrenheit, which means if we've got a heat pump with an electric duct heater as the backup for when it's too cold for the heat pump to operate properly, that heat pump has to have a control that keeps it from operating when the outdoor temperatures are above 5 degrees Fahrenheit. And hey, good news, this is pretty commonly done. Um, the parts are easily accessible, right off the shelf components, the minimal extra cost. I priced it out at less than $100 in parts. So it's not a big deal, but it is something to remember and to make sure we're doing to be in compliance with the new code. Here's some common duct mistakes. We're almost through with the workshop. Thanks for hanging in there with me. I just wanted to outline a few of the common mistakes that we see in the field. So starting at the top, designing a duct system without performing a room-by-room heat loss calculation. So without even this basic minimal step, just sort of approximating the right sizes of branch ducts and guessing at the size of the register based on the size of the branch duct. Um, that's not really getting us where we want to be. Locating ducts outside the thermal enclosure, for example, in an attic or crawl space. Um, I know sometimes this seems like a solution and there just doesn't seem to be any other way to do it, but consider if it's new construction, really consider that the envelope might be better than we think it is, and maybe we don't have to go all the way out in that floor above the garage to get to the window at the end of the bonus room. You know, maybe there's another option. So please don't do that. Failing to provide a return air path for every room in the house. So being able to close off doors and not allowing return air to get back to the furnace. Undersizing the returns. Speaking of returns, those ducts should be at least as large as the supply ducts. Um, Using framing cavities, don't do this. We talked about this, um, like panned joist bays or stud cavities. And this includes bathroom sink vanities. I see a lot of people, they just come up through the floor and they don't even put a register on it. There's just like an open boot in the floor under the bathroom vanity. And then they put a register in the toe kick of the bathroom vanity and they expect that little, cabinet is going to act as a plenum. Doesn't work very well and it leads to a lot of duct leakage and failing to seal all the ducts. So sometimes, we see that the ducts are sealed where we can see them, but the tops of the ducts aren't sealed where we can't see them and where people can't reach them. So sometimes it means assembling sections of ducts on the ground, sealing them up, and then attaching them to the main trunk. And here's some challenges. I think, one of the biggest challenges is the underappreciation of duct design. And contractors aren't receiving feedback, right? So they don't understand. I mean, they only know when something's really dramatically wrong or when the customer's really unhappy. But they don't know if the work is sort of not performing as intended. Um, Failure of integrated design, that's sort of like the builders and the HVAC contractor walk through the job, and then the HVAC contractor just subs it out to a duct sub, and no allowances have been made for where the ducts are going or how we're going to get from here to there. Or remember that picture with all the elbows and the big steel beam? Like that kind of thing is a lack of integrated design. Nobody brought, Nobody thought it through at the beginning, like when the building was still on paper and said, well, how are we going to move ducts from there to there? Um, and what's the problem? Again, contractors aren't receiving that feedback, and as a result, they don't think that their standard practice is substandard. Right? They don't see it as a problem. Um, Integrated ventilation is a challenge. To get it right, at a minimal, we're going to need um, to do dedicated return air, dedicated stale air pickup from bathrooms and kitchens. The best thing is the injection port, like we talked about. Proper installation, of course, all the plans are just plans, and then in the real world, things don't get installed the way we thought they were going to. Nervous homeowners. A colleague of mine was just telling me a story about they had a duct design done by a very well-respected engineering group. They designed a great duct system that was really appropriate for the super low-load home. Um, and then when the ducts started going in, the homeowners are pointing at the duct systems, going, "That's too small. Those ducts aren't going to work." Um, so they were nervous because they didn't know that regular sized ducts would have been vastly oversized for their home that needed 500 CFM. And again, we talked about lack of commissioning. We really got to get on this one. This is something that installers could start doing today that would make a huge difference. So let's consider that. Here's some references. Um, these are links to more information on duct design. I think if you're interested in the topic and you want to know more, and some of these articles have great graphics and make it really easy to understand. Um, I do also, if you're interested in this, I recommend, highly recommend taking the ACA design course that I mentioned earlier. Here's where you can get to it. Um, if you're really going to do this, consider taking the design course and buying some software and really doing it proper. Thanks for staying with me. Feel free to reach out to me directly if you like more info or if you have any questions about the presentation. And just thanks very much for joining me today and sticking with it till the end.